Hey gang, reliability and validity for this video. This is a dual for 6620 and the 699 course that I'm 6999 course I'm teaching. Uh, you know, I started thinking about it, and validity and reliability has. And this, I'll tell you, this is going to be a short video, but reliability and validity, I touched on those things in maybe far too much detail across, I think 5 videos. What I wanted to do here is to give you a final video that just kind of ties it all together, the things that I want you kind of definitely have on your radar. And, if we have reliability, validity issues, then we'll dive into the particular part that we have and learn more about that particular part for our research. But I just want you to have an overview of the different reliability, validity measures that we run into. So let's go through this real quickly. Guys, I know it's going to be tempting not to watch the video. I encourage you to, because I want you to be able to differentiate between certain things, okay? So we're going to look at reliability first. Reliability to me is just about consistency. Do our test results give us consistent measures as we repeat the measurements across the same same subjects, and the underlying reliability, I should say the underlying theory of reliability is what we call classical measurement theory. So think classical test score theory that we've talked about in previous videos. Perfect reliability, we could say if a measuring instrument were perfectly reliable, then it would correlate perfectly with the true scores. And if you measure an object or an event twice and the true scores do not change, then you would get the same measurement twice. So in other words, we would have a perfect correlation of 1. Well, we know that's not the way it happens. We know the measurements contain random error. We should know that the mean of the errors is equal to 0, because the positive errors and negative errors tend to cancel out. Speaking of, some measurements have a error that makes the observed score lower than the true score. Some have error that makes the true score the observed score higher than the true score. So guys, keep in mind the last bullet there. Random error does not affect the mean. The mean will be 0. Random error affects the variance. And the more random error that we have, the more that the observed scores vary from the true score, then we clearly and obviously would have an increased variance in our measurements. Okay, and it's just, I mean, if someone's true score on an IQ test is 110, and they get 108, 109, 111, 112, 108, well, that's not varying much. So we would expect the variance of the errors to be relatively small. But if someone's IQ is 110 and they get a measurement of 102 and 128 and a lot of variation, then again the means are going to be equal to 0, but the random error has a lot more fluctuation or variance in, so the variance of the measurements would be higher. Guys, estimating reliability, the reliability of a test is always unknown because the true scores are unknown. For example, in my Math 1500, students are all the time. Can we talk about IQs? Because it's just a classic example of normal distributions. And they all the time, Dr. Darbo, what is your IQ? And I'm like, well, I don't know. And they're like, well, you haven't taken a test? And I said, well, actually, I've taken about 10 IQ tests. Actually, it turns out I've actually taken 11 or 12. But my score has always been different. But a lot of people go out and take an IQ test, and they just assume that on that particular day that their observed score, the test result, is exactly what their true score is. And so they're just assuming that they are just perfect little beings walking around where there's no error of measurement in their lives, which I'll tell you is highly unlikely. Okay, So guys, we don't know reliability because true scores are unknown, but we can certainly estimate reliability. Now, some of the methods that we use to estimate reliability, one of the most common and straightforward is just test retest. So we give the test, we administer it one time, and then at some other time we administer the test again. We use the straightforward Pearson's correlation coefficient as the index of correlation, hoping for a correlation of 0.7 or higher. And we control for the practice effects and examine that because the mean and standard deviation should not change much. And we can examine that with just simple t-test and dependent samples t-test. Alternate parallel forms of reliability. Are the forms equivalent and highly correlated? Just use the correlation coefficient as an estimate of the reliability here. So, in other words, we have two different forms, and I do this a lot in my classes. I have Form A and Form B to minimize cheating, and I may need to assess the reliability. Are the responses consistent over Form A and Form B? So that would be a situation where we'd have alternate or parallel forms reliability. Split half reliability is the basis for probably the most commonly reported types of reliability, although split half per se isn't. But it's motivated by the natural issue of parallel forms or the problems of parallel forms, convenience, practice effects. But it splits the test into two random components. So if we have 50 questions, we may take all the odd questions and put them in one half, all the even questions and put them in another half, and then we correlate the responses on the two halves. Now the problem with that is addressed in the Spearman-Brown reliability, that when we take a total number of items, again as an example 50, and we split this into two halves of 25, a natural issue in reliability is that when we reduce the number of hours, naturally the reliability coefficient will be reduced. All right, so what most people do to address that is they do what's called Cronbachs Alpha. Cronbachs Alpha claims that it will it examines all of the possible ways that you could split a test into two equal halves, and it'll calculate the mean of the coefficients, and so it'll give you the average of the reliability coefficients for all possible split halves of a test. Maximize lambda 4, kind of a new kid on the block, if you will. What it has found is do Monte Carlo simulations that the reliability estimates tend to underestimate the true reliability. In fact, most reliability estimates, such as Cronbachs Alpha, serve as a lower bound. And what it does here is at least it claims to calculate all split half, and it just selects the largest one. So Cronbachs Alpha actually claims to split into all possible halves, calculate the reliability estimates, and take an average, where the maximized lambda does the same thing, but it just takes the largest of all the reliability coefficients. Moving into validity, the other part, validity, focusing here on construct validity, is just how well does our test measure what we claim it measures. If I'm giving a placement test, how well does my placement test measure someone's potential to take the particular course that we're enrolling them in based on the results of the placement test. Just going to run through quickly a few things about validity, face validity. This is where experts in the field get together and agree that the instrument is truly measuring what it claims to measure. Happens a lot. The thing that I always find kind of entertaining about face validity is sometimes you get experts, and I saw this in a recent department meeting, sometimes you get experts that just don't agree. So that's an interesting dynamic to face validity. Content validity. Content validity, pretty much we've got some larger population for the constructs that we actually want to be measuring. We draw a sample from the population, and we ask a team or a panel of experts to judge how well the representative sample is of the population. Let's say we wanted to create a test on assessing skills of taking derivatives. Well, there's an entire population of possible test questions for assessing one's derivative taking skills, and so a team of experts would get together and see how well the questions that were chosen actually match up with the entire population. So face validity and content validity, I always think of those two as experts in the field driven. Now, on the other hand, criterion-related validity determine how the outcomes on a test are related to other things. And I'm going to run through some different types of validity, but as an example, since I teach statistics, let's say we'd like to assess criterion-related validity for a statistics test. So let's just go through each part of the validity issues and talk about how we may implement that. The first one I want to talk to you about is concurrent validity, and concurrent means just something measured at the same time. Current, okay? I don't know really why they did put the con in front of it. It's just current validity. Our instrument scores strongly correlated with scores measured at the same time. So you would think that students who just finished a statistics class would score higher on a test than students who have never taken a statistics class, again measured at the same time. And we might find a strong correlation between a test score and some other current level of performance that are given to students, again, at the same time taking a statistics course. Some of this stuff is so simple. It really is, but it's just knowing the difference, guys. Predictive validity is just as you would think. Can our test does our test correlate with some sort of future performance? We might be interested to see if there's a strong correlation between a test result and performance in an occupation in the future that requires the use of statistics. And there could even be we could examine a strong correlation between a test result and maybe test questions on a GRE that claim to assess some knowledge of statistics. Convergent validity is our test highly correlated with certain constructs, logical thinking, abstract reasoning, verbal ability, mathematic ability, certain constructs that we would think would have some natural relationship to the generalization of skills that may be required to take this particular statistics test that we're talking about. Discriminant validity is just opposite. We don't want our test correlating with things that it shouldn't correlate. So is our test not highly correlated with constructs that it shouldn't highly correlate with? If there's a relationship between our test results and someone's love of burritos, I'm going to question well, that would actually be kind of cool. Now I think about it, but no, it wouldn't be cool. That would be that would really raise validity issues. If we're trying to create a test, again, validity says that our test measures what it's supposed to measure, and if it's actually measuring something else, then we have obvious discriminant validity validation issues. Well, gang, that's it. One of your favorite videos, right? Because it was one of the shorter ones. So that's all I got for you. We got a couple more videos coming up, and otherwise we're about ready to wrap up the semester and get in the final project. So take care, guys.